if I take a look at the next one, it says a radioactive isotope has a half-life of 500 years, and there is a lab sample that contains 53 grams of the substance. If the sample would have had an initial amount of 300 grams, how old is the sample? Okay, so the first thing we're going to do is find the K value for this. So this is really a two-part problem here. I'll split this into two parts. The first part, I'm going to use my equation. I know the initial amount was 300 grams, e to the negative k, because it's to k this time, so I have to slap a negative in front of my k value. And I want to find k, so I'm going to use the half-life. This is where the half-life comes in. The half-life is 500 years. So if I plug 500 in for my time, after 500 years, I'll have half the amount of the substance. So instead of 300 grams, I'll have 150 grams. And now I can solve this for k. So I'm going to divide each side by the 300. So I get a 0.5 equals e to the negative 500k. I take the natural log of each side. Natural log and e cancel. And now I'm going to divide by this 500. So the k value that I get here, I'm going to plug this into my calculator, is a 0.001, we'll go 39. That's where I'll round it off, okay? And it's important to keep a couple decimal values here to make the second piece of this thing a little bit more accurate. When I do the second piece, again, I'm talking about a 300 gram sample. E to the negative k, well, now I have the k value as the 0.00139. Time is the thing that I want here, or that I need. That's what I'm looking for. And I want to know when this thing is going to equal 53 grams. That's where the 53 grams comes in. And now I'm going to solve this for t. I divide each side by the 300. And I'm just going to leave this as a fraction. Okay, as the 53 over 300. That's the easiest thing to do. And it's the most accurate thing to do. And now from here, I'm going to take the natural log of each side. So again, I'm still going through the same process that I have in the past couple examples. I'm just going to be plugging this fraction into my calculator. And now I divide. So I plug it in, find out the t equals. Like 1,247.1. And again, that's in years this time. And it's in years, and that's essentially why I've found this k value. This gives me the k per year. Okay, it gives me that value in a time that makes sense. Okay. If we look at the next one, it says an organization believes the game preserve has a carrying capacity of 1,000 animals, and the growth model of the herd will follow this logistics equation, where t is measured in months. Okay, so in months this time. And we want to know what was the initial size of the population. Well, again, remember the a value here, the 9, is a constant term associated with the initial amount. If I want to find the initial amount, it just means that I'm plugging a 0 in for time. Remember, the initial amount is when t equals 0. So I'm going to plug that in. So I've got 1,000 over 1 plus 9 e to the negative 0.165 times t, which is the 0. And when I plug this in, I get 1,000 divided by 1 plus. Well, this whole thing right here becomes a 0. And e to the 0 power equals 1. So what I have here is 1 plus 9, which is just a 10. So the initial population is 100. Okay? In part B, it says, what is the size of the population after 24 months? And again, this was in months, so my units already match. So I'm just plugging this into my calculator. I'm plugging in that 0.165 times the 24. I'm raising e to that power, and I'm just plugging it in. So again, when I plug this into the calculator, in fact, let me show you. I'm going to take order of operations into my own hands. So I'm going to do e raised to the power, and that's going to be of the negative 0.165 times the 24. I'm going to hit enter, and then I'm going to multiply that by the 9 and hit enter, and then I'm going to add 1, hit enter, and now I need to do 1,000 divided by this value that I have. So what I do on the calculator is I hit the 1,000, and then I divide by second, and then the negative sign brings up this ANS. It means I'm doing 1,000 divided by the previous answer, and I hit enter, and it gives me 853.5, so I'm going to round it to 853.4 to the nearest animal, or sorry, 854 to the nearest animal. Okay, that's it. If I look at the next one, says the engine of a car cools at a rate of 13% per hour. If the temperature of the engine is initially 350 degrees and the outside temperature is 32, what will the temperature of the car be in 3 hours? All right, so this is where we're going to use our formula for Newton's law of cooling, which remember is U of T, which is the temperature of the object, equals T, which is the surrounding temperature, plus U of 0, which is the initial temperature of the object, minus the surrounding temperature again, times e to the negative kt. All right? And I'm just going to start plugging in what I know here. I know the outside temperature, the surrounding temperature is 32. I know that the initial temperature of the engine is 350. I know that, again, the outside temperature is 32. The K value is the rate, which is going to be a negative 0.13, and that's per hour, so my time has to be in hours, which it is, so times the 3. So again, this is a job for my calculator, so I'm just going to plug it in here. And once again, my recommendation is to take order of operations into your own hands. So when I plug this in, I get a 247.3 degrees. All right? The next part of this thing asks me, well, if the engine needs to cool to 120 degrees before you can perform an oil change, how long do we have to wait before we can get to work here? All right? So again, I'm going to plug in what I know. I know that the temperature is 32 degrees. Not that we'd want to do an oil change outside in 32-degree weather, but sometimes that's just the way it goes. The initial temperature is 350. The rate is still the 0.13. Time is what I'm looking for this time, so that's t. And I want to know when this thing's going to equal a 120. Okay. So now I'm just going to solve this. I have to isolate the exponential part of the function. I'm going to subtract the 32 from each side. So let's see, that's going to give me an 88. Over here, I can go ahead and simplify what's inside the parentheses a while because I'm going to have to divide by that thing. So I'll subtract those. That's going to give me, I guess I don't need the parentheses here, 318 times e to the negative 0.13t. And now, just like I did before, I'm going to divide by that value that's out front. I'm not going to bother reducing this thing. I'm just going to leave it the way it is, just because I know I'm going to be plugging this into the calculator. So I've got the 88 over the 318 equals the e to the negative 0.13t. Now I can take the natural log of each side, which cancels with the e. I've got the natural log of 88 over the 318 equals a negative 0.13t, and I divide. And again, it's just a job for my calculator, so I plug it in. So it looks like I've got 9.8 0.88, all right? And that's hours.